Okay, so here's the second part of this exercise. We're going to perform interpolation. In case you have forgotten what interpolation is when we estimate a point between two points. Okay, so here again we're dealing with dissolved oxygen, and what's going on is that we have points, but it's impossible for us to measure every single point on that lake. So instead, what we do is we interpolate and find out what the regions of concern are. Okay, so we're going to perform interpolation. Hopefully this will be 20 minutes. We ran a little bit over last time. Let's see how this goes. So we're going to perform interpolation. We're going to open a geostatistical wizard and choose an interpolation method. After that, we're going to explore and configure kernel interpolation with barrier options. Let's see, which is interesting. And then we're going to discover how bandwidth changes the effect of the interpolation. And when we finish that, that should be it. Okay, so we're looking at what is it? 1, 2, 3 little items. Not too bad. Not too bad. So we're going to open that geostatistical wizard and choose an interpolation method. It says if necessary, open your Chesapeake water quality project. Here it is pinned on mine, so I'm just going to go ahead and click on it. And it comes right up. Let's see, on the ribbon, click Analysis. And in the Tools group, there's a Tools group. We're going to click on Geostatistical Wizard. So we're going to look for Geostatistical Wizard right there. Okay. And we have the wizard opens, showing various interpolation methods. In step 3, it tells us that for interpolation with barriers, so interpolation with barriers, we're going to choose the kernel interpolation. Click. Let's see. Next, we'll create a result by interpolating the major value field of the dissolved oxygen layer using the Bay layer as a barrier. So in the geostatistical wizard, we're going to choose the following for the data set right here. For source data, it's going to be dissolved oxygen. That makes sense. Data field is going to be a measured value. Okay. Source data set is going to be the Bay. We're going to click on Next. Okay. It says you are notified that 2 or more samples exist at the same location. You are prompted to select a method for handling the coincidental points, right? Confirm that use mean is chosen. So we're going to use a mean. Let's see. This will average dissolved oxygen values for all measurements at each location before proceeding with the interpolation. Other options provide the ability to ignore all coincidental points. Let's see. Only use the smallest of the coincidence points, the minimum, and only use the largest, use maximum, or use all of the coincidence points, include all. So we're going to click on Next. Okay. like that's it. So all we're going to do here is click let's see. Oh. Okay, so here we have a few things to look at. We have the kernel, fifth order polynomial. Okay, as in type of interpolation, uses a fifth degree polynomial, which is a complex interpolation. It's a very good interpolation. We have the output surface. Okay, the option allows you to switch the preview surface from prediction to standard error of prediction and vice versa. Okay, in other words, it can give you either give you a straight prediction or an error in there. We have the bandwidth. The bandwidth value controls the radius of the scaling circle in the preview surface, which is right here, right? For this data, the bandwidth is measured in meters, and the default is provided by the software based on a simple optimization. The bandwidth should be 37,540.48. It is. We're supposed to review the identify results section, which is there right here. Let's see. For the X, we got to make sure that it's 370,000 meters. So I'm going to copy and paste that so I don't make a mistake. Okay. And for the Y, it should be 4,220,000. And I'm going to make sure to paste that so I don't make a mistake. There it is. Okay. Looks good. The previous surface moved a little bit. Okay. Okay, now you are told to zoom into the circle here. So with your mouse, you can move it around and zoom in like so. And your author makes you pay attention to some things going on here, like these 4 points right here. Okay. It says 4 points at the upper right of the searching circle are not highlighted in any color. These points are excluded as their water distance is further than the bandwidth from the predicted location. So this bandwidth told us that these 4 points are too far away from the water to matter. And then we have these blue lines right here. I don't know if you can see them. Maybe if I can make it bigger. But you have these blue lines. Okay. As is the blue line, and the following image represents the water distance from one of the points to the predicted location. Since the length of the blue lines exceeds the bandwidth, the point cannot be used as a neighbor. So again, you know, we're making sure that the points that we're measuring are representative of something that will give us good data. Okay, so that's looking pretty good there. Okay, and now we're in the last part of this. Discover how bandwidth changes the effect interpolation. So what we're going to do is we're going to change the bandwidth to 1,000. 10,000. Hit enter. And you can see what happened to the circle, 1,000 meters. Let's see. On the preview surface menu, we're going to click Reset View. This puts it right back in the center. Okay. Let's see. Now we're going to change the bandwidth to 100,000. We're going to put a 0 in there. You can see what happened. Okay, the circle becomes 10 times bigger. Okay. So by increasing the bandwidth, you can introduce many neighbors that can be used in the calculation. However, more neighbors are not necessarily better. By including so many neighbors from the lower and upper parts of the bay, you have made the surface too smooth. The contour lines now indicate a gradual change that is unrealistic for dissolved oxygen values. So the point that the author is trying to make here is that when you're doing interpolation, this bandwidth, how much you incorporate into your data set is the most important thing that you can do. Okay, for bandwidth, we're going to click the Optimize button. There we are. That's where we started. Click Next. Okay. This is a geostatistical wizard, updates and displays the cross-validation window. This is the final window of the geostatistical wizard and contains numerous graphical numerical diagnostics that allow you to determine how well the interpolation performs. So we can see, let's see, measure regression line, reference line, error, standardized error, distribution, predicted, quite a bit of information there. Okay, we're going to click on Finish. It says the method report window opens, showing a summary of interpolation and the settings you're applying to your data. Click OK. Okay, and the geostatistical wizard closes, and a layer named kernel interpolation is added to the map. Is that awesome? So now what we have done is we have created an interpolation of oxygen concentrations throughout the map, and they're color coded. Okay. In the contents pane, here we are again. Turn off the dissolved oxygen layer. So here's the dissolved oxygen. We're going to turn it off. Okay. Zoom to the full extent of the Chesapeake Bay. So we're going to zoom. Oop. That's good enough. On the map, red and orange represents the highest average dissolved oxygen levels. Note that the most of these high values are in the southern section of the bar near the Atlantic Ocean and at the tips of the inlets. Okay. The lowest levels, indicated by blue and green, are in the middle and upper parts of the bay. In the contents pane, expand the legend of the kernel interpolation layer. So here's your kernel interpolation layer. We're going to expand it. And there shows the ranges. It says, the range of the values of the different colors indicate that significant areas of the Chesapeake Bay have predicted average dissolved oxygen levels below the unhealthy level of 5 milligrams per liter, but no locations appear to have had average levels near that fatal level of 0.2 milligrams per liter in the summer of 2014. This means that the values are observed in the histogram chart that were below 0.2 milligrams per liter must have persisted for short periods of time, and the average levels of dissolved oxygen levels did not stay near the fatal level all of that summer of 2014. In other words, the bay is doing okay. What are we going to do now? We're going to save the project, and I wish we could save it. That's a new project, but I don't think we're being given that option here. Let's see. Ah, here we go. Save as. So save as, and go ahead and click on the oh, this darn thing. It always saves here. Go ahead and save as a Chesapeake water quality, but put a 2 in there so you know that it's your second map. And then go ahead and save it. So it'll be that second map that you have saved. So effectively, I want a map for each one of the sections. Okay, so that's it. I hope that was short enough. Thank you.